Hi, we're from Group 1E and we're presenting our ECC3161 group project titled Passive Thermal Sensor System. So this project focuses on the design and development of a non-contact body temperature monitoring system based on infrared thermal sensing. The system operates by detecting heat radiation emitted from the human body and converting it into electrical signals for further processing. It integrates three main stages: analog signal conditioning, digital logic verification, and microprocessor-based control. To improve detection reliability, a majority voting logic is implemented, where at least two out of three sensors must detect a high temperature condition before an alert is generated. So the system provides both visual and audible feedback through an LCD display and a buzzer, allowing users to clearly identify whether the system is in a normal or alert state. This slide illustrates the overall system architecture of our system, which is divided into three main stages: the analog stage, the digital stage, and the microprocessor stage. In the analog stage, three infrared thermal sensors detect heat radiation from the environment. Then each sensor output is passed through an amplifier and a filter to strengthen and stabilize the signal. A voltage comparator then converts the conditioned analog signal into digital high or low output. In the digital stage, the three digital signals are processed using AND and OR logic gates. A majority voting logic is applied so that the system only produces a valid output when at least two sensors detect a high temperature condition. This helps to reduce false triggering and improves overall system reliability. Finally, in the microprocessor stage, the verified digital signal is received through GPIO inputs. The control program evaluates the signal and determines whether the system should remain in normal state or enter an alert state. So, based on this decision, the microprocessor controls the LCD display and the buzzer to provide appropriate visual and audible feedback.
This flowchart illustrates the control logic implemented in the microprocessor stage of the passive thermal sensor system. The process begins at the start block where the microprocessor is powered on and ready to execute the program. The system then proceeds to read the output from the logic gate. This value represents the process result from the digital circuit stage, where multiple thermal sensors are evaluated. The logic gate output is a single binary value, either 0 or 1. Next, a decision is made to check whether the logic gate output is equal to 1. The decision block determines the system state. If the output from the logic gate is not equal to 1, meaning no high temperature condition is detected, the system turns the buzzer and LED off, indicates normal operation. The process then moves directly to the end state. If the output from the logic gate is equal to 1, the condition identifies a high temperature condition. In this case, the microprocessor activates the buzzer on and LED on, providing both audible and visual alerts. After triggering the alert, the process also proceeds to the end state. Overall, the flowcharts demonstrate the microprocessor make a simple and reliable decision based on logic gate output to ensure timely alerts during high temperature conditions.
Assembly programs implements the control logic for the passive thermal sensor system at the microprocessor stage. So the program begins by including io.inc file, which provide input and outputs macros such as getDesk, printstream, and new line. So this macro simplify interaction with the user through the SASM environment. The program execution starts at the main label. The step frame is initialized by copying the step pointer into the base pointer. Step pointer is ESP and base pointer EBP to ensure the stable execution. In the input section, the instruction get dash for sensor input with a 32 bytes decimal value from the SASM in tab input tab and store it in the variable sensor input. This value represents the digital output from the logic gate stage, where 0 indicates a normal temperature condition and 1 indicates high temperature condition. Next, the input value is moved into the EAX register and compare with the value 1. If the comparison is true, the programs jump to alert state, otherwise it continues execution in the normal state. In the normal temperature state, the program stimulates normal operation by displaying normal temperature on LCD and indicates that the buzzer and LED are turned off. If the value is 1, the program stem will be enter the alert state. In this state, the system will display LCD LED high temperature, buzzer on, and LED is on to stimulate a warning condition. Finally, the program terminates by clearing EAX register and return control to the operating system. The variable sensor inputs is declared in the BSS section to reserve 4 bytes of memory to store the input value. Overall, this program verifies that the microprocessor correctly responds to digital signal from the thermal detection system and control the output indicates of the code accordingly. So right now, if I enter the 0 in the input tab and then I will click the build and run, the LCD, the output will show the LCD normal temperature and buzzer and LED will indicate off. If I change the input into 1 and click the build and run, the output will show LCD high, alert high temperature, buzzer on, and LED is on. That's all from us. Thank you.
To wrap up things up, our project has successfully realized a robust and non-contact body temperature monitoring system by integrating the 3 core modules for sensoring, for logic, and controlling. We have built a pipeline that transforms raw infrared heat into actionable safety data. As we saw in the control logic assembly implementation, the microprocessor acts as final decision maker is efficiently pull the GPIO inputs and instantly toggle the system state when this is displaying a normal status or triggering the LED and buzzer during an alert state. The software ensures uh, an immediate response. Furthermore, this project supports SDD8 decent work and economic growth by automating the detection of hazard thermal conditions. The system minimizes risk to personnel and equipment. This proactive approach to safety reduces downtime and prevents accidents, fostering a safer and more productive, economically sustainable industrial environment. That's all from us. Thank you.